So welcome back. We're going to talk about fluid dynamics, and the first thing we're going to try and distinguish between is laminar and turbulent flow. So we assume that a fluid flow is non-viscous. That means it's not syrup. You're thinking about water or something like that. Don't think about syrup or tar, because that's too complicated. It's laminar flow. That means that, well, we're going to define down here. It means that basically everything's flowing without turbulence. Things are flowing in kind of like, not necessarily a straight line, but things are kind of staying level with each other. And the flow is irrotational, and I can never remember what that means. It's like, so I need to look it up, because I get to this point, I can never remember what it means. And then the fluid is incompressible, and just means that the density can't change. Okay. And we have laminar flow. Each particle of the fluid follows a smooth path. If you look at this diagram down at the bottom, it's smooth paths. The path of different particles never cross each other. You don't get particles crossing paths. And the velocity of the fluid flow at any point remains constant in time. Now, that's not saying that the velocity here is the same as the velocity there. It's not saying it's the same all over. It's saying at any point it stays the same in time. It's not spatial constancy. It's temporal constancy. It stays the same in time. And the fluid flows at lower velocity. That's how you get it. If you keep the velocity low, you'll tend to have laminar flow. Let's say we don't keep the velocity low. We turn up the velocity. Well, particles do not follow exactly the same path. You can kind of see it here. There's a jumble of particles. If you're in front of me, it doesn't mean to say that I'll stay behind you. We could go in different directions. Whirlpool regions exist. The path of different particles do cross. I might be 5 people away from you at the beginning, and we may end up on opposite sides to each other. And then the velocity of the fluid flow at any point changes in time. I can pick a point, and it's fast and slow, and slow and slow, and fast and slow and slow. Like a gusty, blustery wind is like that. And you get that by having higher fluid flow. There's a thing called the Reynolds number, which you look out for. And if you're below the Reynolds number, and I think you're laminar. If you're above the Reynolds number, I think you're turbulent. This is a real problem. This is difficult to model mathematically, but it occurs in nature. It's not so much we want to create it, although we might want to create it. But it's like it tends to be something we have to deal with. So, few questions. Identify the kind of flow when particles cross paths would be what? Could be turbulent. Identify the kind of flow when the velocity of flow of a specific point never changes. Laminar. Identify the kind of flow when particle constantly follows the same leader. Laminar. It's like laminar flow is like, second grade. Turbulent flow is like high school, getting people to move around. I don't know about your high school, but people just used to there was no line. People were just as a cloud going to the classroom and the like. There are 2 things that we can deal with in terms of fluid dynamics, and they're both to do with laminar flow. And the first is very straightforward. It says that fluid can neither be created nor destroyed within a pipe system. So if I imagine, if I imagine there's a little bit of fluid there, and the bit that flows in must equal the bit that flows out. And so the volume per second entering must equal the volume per second leaving. That's the way it works, yeah? So the volume per second is equal to the area times the distance per second, which is the area times the velocity. And that's what this is saying. It's not saying area times volume. It's the area of the inlet times the velocity at the inlet is equal to the area at the outlet times the velocity at the outlet. Okay?
So the flow is related to energy?
I'm sorry?
He said earlier that the fluid cannot be destroyed or created.
Said the volume of fluid can't be created or destroyed, yeah.
The volume of
Yeah, you got the same. So, pipe has an entrance of 8 square meters. It has an exit of 2. What's the flow? There's a flow in. What's the flow out? So, you don't have to draw a fancy diagram. This is 8 meters squared. This is 2 meters squared. This is 5 meters per second. A1 V1 is equal to A2 V2. This is called the continuity equation. You know, I'd love it if you learned what the equations were called. Because when you get into talking to people later on, they're not going to say, do you remember A1 V1 equals A2 V2? They're going to say, do you remember the continuity equation? And if you know that equation, but you don't remember what it's called, you'll say no, and they'll think you don't know the equation. So if you know what the equation's called, it just helps, you know, in terms of the language. It's like you know the names for the different players on a sports team. You don't say, you know, that person who runs backwards and forwards near the back of the court. You call them, what, a guard, I guess? I don't know. I don't know them. I don't follow sports, so I'm not in that community. But that's the thing. And if I talk to a sports person, they'd roll their eyes and put me to one side, yeah? Well, I don't want engineers to roll their eyes and put us to one side. So let's learn the language. Okay. So this is going to be 8 times 5 is equal to 2 times V2. So V2 is equal to 40 over 2, which equals 20 meters per second. 20 meters per second. And again, I can make it interesting by giving you the radius rather than the area. Or I could give you the area in non-standard units, you know. Then the next thing is good old Bernoulli's equation. And Bernoulli's equation looks horrendous. But it's actually if you're kind of like, you're comfortable with like an impressionistic approach to equations, you can get it. So if you look at it, there's pressure. This is, well, it reminds me a bit of kinetic energy, half mv squared. Well, no, it's half rho v squared, v's velocity. And this reminds me a bit of potential energy, mgh, no, rho gh. So it's kind of very reminiscent. So I kind of remember it that way. It's to do with pipes which have different input velocity, different output velocity, different areas, different pressures, different heights. So it's the much more detailed equation. We say a pipe's entrance is 2 meters above a table. And the water pressure is 90 Pascal. The water speed is 8 meters per second. The exit, or the density equals 6 kilograms meter cubed. The density is 4 meters above. The pressure is 50 Pascal. And I want to show that the flow, V, is equal to 6.1. So I go P1 plus a half rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. The rest is plug and chug. I mean, it's basically 90 plus 1/2 times the density of the fluid, which is 6, times the velocity squared, which is 8 squared, plus 6 times 10 times 4 is equal to 50 plus a half times 6 times, I want that v, so I'm going to call it v squared, plus 6 times 10 times 4. Oh, I messed up on that. That's 2 on that side. I'm sorry. That's 2. This is that side. So that's 2. So 90 plus 3 times 64, 180, 192, plus 120 is equal to 50 plus 3v squared plus 240. So that's 192, 282, 382, 402. Can you check me on that? Yeah. Minus 290 is equal to 3v2, v squared. So that's going to be 112 is equal to 3v squared. So v squared is equal to 9 carry 2, 7.3. So v is equal to the square root of 97.3. So v is equal to, that's not right. Let me just double check.
That's 112 divided by 3, right?
Is it 112 divided by 3?
Yeah.
Yeah, that's where I'm wrong, aren't I? 9.73. No? 37.3. 37.3. So that's going to be 6.1 meters per second. So it looks horrendous, but it is literally just learning the equation. And just remembering, it looks a bit like kinetic energy, but there's got a density in it. Looks a bit like potential energy, but it's got a density in it, and we've got pressure. What you might want to do is you might want to just to make yourself comfortable, density is kilograms per cubic meter, and velocity squared is meters squared per second squared, which gives me kilograms kilograms per cubic meter, kilograms over meters second squared, and just confirm that that is actually the same as pressure, which is newtons per meter cubed, which equals kilograms kilograms meters per second squared divided by meters cubed, which is kilograms over meters second squared. So it works out to be the same unit. So just satisfy yourself that that's got the same units as that, as the same units as that. Okay. And there we have it. So let's close it there. Next time we'll continue.